All right, well, why don't we get started? So just first, I really want to thank Quinlan for being here. It's very kind of you to take your time off on Saturday. And just a brief background is this is just a snapshot of some of his background. He's a geoscientist with Quaise Energy based in Boston. He earned his bachelor's in geosciences and political economy from Williams College in 2020. Joined Quaise in 2021. His work includes enhanced geothermal systems resource assessment and integrating geologic and socioeconomic data using GIS tools to inform Quaise's geothermal leasing strategy across the United States and beyond. And he's also developed 3D geologic models for Quaise's commercial pilot project Obsidian and worked as a well site geologist near Austin and Newberry Volcano, Oregon. So welcome, Quinlan, and I will turn it over to you to start your presentation.
Thanks, Roger. I'm really glad to be here today to talk about Quaise and geothermal and some of our policy priorities. We're supporters of Citizens Climate Lobby's mission, and yeah, personally, just glad to speak with some folks who are passionate about these issues, like I am, and everyone else at Quaise is.
And
Um,
before we start, if I could request everybody to mute themselves, there is a little bit of background noise going. Um, so if you would please do that, and we will get into Q&A later, and we'll talk about that later.
all right. Like I said in Roger's intro, Quinlan Byrne. I'm a geo scientist with Quasi Energy. I work mostly on our leasing and project development work out of our office in Boston, Massachusetts. Currently, I'm out in Oregon, 45 minutes south of Bend, on site at our first commercial project at Newberry Volcano called Project Obsidian. We also have a big office down in Houston where the majority of our company is based, working on the engineering challenges associated with our technology, millimeter wave drilling, and also a field lab out in Austin where we're testing some of that technology. So I'll just go do some background on geothermal and the sort of current status of the industry. I think geothermal is kind of one of those words that obscures more than illuminates sometimes because it encompasses so many different types of technologies and energy solutions. The main categories are heat pumps, which is sort of smaller scale heat exchangers in the shallow ground that are taking advantage of Earth's ambient temperatures, hydrothermal system like a geyser, and taking that steam out of the ground, using it to spin a turbine to generate electricity. Next gen technologies are pretty broad, but include things like enhanced geothermal systems where you're creating a permeable reservoir in rock that is naturally not permeable, or closed loop systems, sometimes called advanced geothermal systems, where you are circulating your fluid through very long laterals in impermeable rock. Um, and superhot rock, which is basically very high temperature geothermal. Um, so, as I said, heat pumps are generally at shallow depths, less than 200 meters below the surface, extracting heat from that sort of background ambient temperature of the ground when it's cold outside and storing the heat down there when it's hot. And this can be done on commercial or consumer scale systems. A lot of people, when they think of geothermal, think of the types of geothermal heat pumps that people are installing at their houses more and more these days. There's also district heating and cooling, and that's sort of split into two categories. The common feature being sharing this system amongst a industrial center or a community. Direct use where you are extracting heat and sort of sending it where it's needed in this network, and a thermal energy network where you are trying to share heat most efficiently between your sites. So maybe you're taking excess heat out of homes and sending it to a greenhouse that's connected to this network. Conventional geothermal is sort of the bulk of geothermal electricity generation, where, as I said, you're going to a geyser or a hot spring and extracting the naturally flowing steam from that system to spin a turbine. There's sort of three categories of geothermal power plants. A dry steam power plant where you're taking steam directly out of the ground, expanding it to spin a turbine to generate electricity, and then putting back that water into the ground when you're done, or evaporating it for cooling. There's flash steam where you're taking pressurized water at very high temperatures, flashing it to steam, and then spinning a turbine and doing the sort of same thing as dry steam. And the last category is binary cycle plants, where you are extracting hot steam or water, running it through a heat exchanger, usually with a organic fluid that has a lower boiling point than water. And that allows you to use lower temperature resources that you couldn't previously, or to use fluids that are very caustic and challenging to deal with the chemistry inside of a turbine. So those are the sort of main buckets. And then in this next gen geothermal category, we have sort of three categories that all overlap in different ways. But there's enhanced geothermal systems, or EGS, which is the sort of popular category right now, where you're adapting unconventional oil and gas technologies to engineer artificial heat exchangers in hot, dry rock. The natural, very low thermal conductivity of rock means that the goal of these systems is to maximize the ratio of surface area to reservoir volume inside of this rock that is starting without any real fractures or surface area for you to extract that heat from. A sort of alternative design philosophy is advanced geothermal systems, or closed loop geothermal systems, where instead of fracturing the rock to create that surface area, you are essentially drilling many nearby laterals, and sometimes injecting thermally conductive sealant essentially into the cracks around the well, to allow you to extract heat from the areas around the well without artificially creating more permeability. The final category, which overlaps with both of these, is super hot rock, where the goal is to get to temperatures above the critical point of water, where water stops behaving like steam and more like liquid water again. And so you get a density increase when you pass this critical point, compared to steam, which means you can flow more liquid through your well at once, which allows you to generate more power from your system. In each category here, we have, so for EGS operators, the one that most people have probably heard of is Fervo, but there's also Sage and Greenfire. In this closed loop AGS category, there's operators like Ever and XGS. And then in the super hot rock category, there's Quaise and Mazama. And there's more companies and developers out there. But these are sort of the ones I think that are most well known. This is a quick slide on why Quaise believes in superhot as the future of the industry. As I was sort of saying earlier, going super hot allows you to flow more liquid at higher temperatures through your well at once, which translates to an order of magnitude more electricity production per well, compared to a conventional hydrothermal system. The challenges here are around the chemistry of the fluid and sort of long-term stability in your well completion and your reservoir design, because these are ultimately dynamic systems that are evolving as the reservoir changes. We think at Quaise this is the only realistic way to get to this $45 per megawatt hour DOE Earthshot number on a broad geographic basis around the country and the world, not just in very high geothermal gradient areas where you have a high grade resource near the surface. Um, this is a little bit on Quaise's drilling, sort of comparing the categories of different drilling. You can see on this not to scale figure on the right, uh, these higher temperatures are pretty inaccessible unless you have magma near the surface or a very radioactive granite near the surface that's naturally producing. What Quaise brings is this microwave-based drilling technology that will allow us to get to the depths in the range of 10 to 20 kilometers or 6 to 12 miles without exponential increases in drilling cost. On the right, there's a figure that's showing sort of the depth and temperature ranges of some of the deepest and hottest wells, and sort of where Quaise stands in comparison to those wells and where we are aiming to go down in that lower right-hand side of the figure. This is just like a little background on our leadership team, our offices, and our investors. I said we have a large presence in Texas with most of our employees in our Houston office down in Pearland, and then also a mobile field lab out in Marble Falls where we're testing the drilling technology on a granite quarry. It's actually the same quarry that quarried the granite for the Texas State House. So kind of a cool factoid we like to share, especially when talking to Texas legislators. We also have this office in Boston. We originally spun out of MIT's Plasma Science Fusion Center because they also use
What can I
this
do, Raj?
gyrotron to generate high frequency millimeter waves or microwaves for fusion
Yeah,
experiments.
no, it's working fine here.
Sorry, Bill, I think you are unmuted right now.
Yeah.
This is a timeline of sort of the company's development status. In 2018, we were founded, spun out of that lab. I joined
I saw that Bill
in
Hurley was also
2021.
host,
And
was host. So,
the company has been sort of plugging away at the research side of things until the last year or two, really, when we have begun to scale up quite a bit more and are beginning work on this project out here in Oregon, which will be our first commercial power plant.
I was just saying,
This is a little bit on gyrotrons and how we use them to drill. The gyrotron is the millimeter wave generating device at the surface that we create this microwave beam with, and then that's transmitted downhole to the rock target at the bottom of the well with a piece of equipment called the waveguide, which is essentially just a corrugated pipe that's tuned to the frequency of the millimeter waves so that you can send them over long distances in the same way that fiber optic is used to send light over long distances. We're also circulating purge gas down to the bottom of the well with the millimeter waves to lift the cuttings from the drilling process. The system is designed to integrate with conventional oil and gas rigs so that we can leverage that workforce and technology that's been in development for over a century now. This is sort of the techno-economic argument we're making, where with conventional drilling, you start to see an exponential increase in drilling costs after 5 or 7 kilometers. That makes it cost prohibitive to reach these high temperatures that are most economic for geothermal power generation. Because our system really just consists of this corrugated pipe with some specialized instruments on the surface that allow us to do measurement while drilling mostly from the surface, we think we're going to have a linear increase in cost because we're not tripping in and out of the hole constantly to fix broken electronics or damaged bits. I have a quick video here of what this process looks like. This is from a year ago, so we're not always drilling this way, but you can see that we are ablating and vaporizing the rock with just the microwave beam. There's no mechanical grinding or scraping of the rock to drill. We do have a sort of scraper bit on the end of the launcher for the millimeter waves, so that we can ensure the whole quality as we're going. Sometimes there's sort of fragments or junk left on the well, created by the microwaves that aren't circulated. Let's just play that one more time. Quaise is testing this technology right now in Marble Falls, just about an hour outside of Austin. This is a drone shot of our site. We've drilled 100 meters last summer, and our goal, I should say, Q3, maybe 26, for a 1 kilometer well, 3,000-foot well with this microwave technology. This year, we've been limited by our supply chain and our ability to create enough of this specialized pipe, the waveguide, to reach that depth. So we would have kept going, I think, to 1,000 meters if we could have, but have not yet been able to manufacture enough of this drill pipe. Last year, we also did a sort of proof of concept integration with a conventional rig that is at Neighbors Drilling, their experimental test site in North Houston. So you can see here, we've basically taken a conventional rig and adapted it for millimeter wave drilling, so that sort of proving out our concept in the field where we would drill with this conventional type of system until the economics start to get too challenging. At that point, we would switch to the microwave-based system. So the idea is not that we're trying to start at some arbitrary depth target where we think millimeter wave will work best. It's really based on the cost that we're seeing, and we make that switch when it's economic to do so. And just to say, that's because conventional drilling is very well suited for shallower, softer rock. And we don't want to reinvent the wheel. This is really just like a new technology to push farther than what's possible. Our long-term development plan, so this is a map from National Lab of the Rockies, or National Renewable Energy Laboratory, that's showing sort of the most suitable areas for enhanced geothermal systems. And we really want to make this a technology that enables geothermal power generation anywhere in the world. There's always a few places where it's probably just never going to be possible, but we think if you can drill to 15 or 20 kilometers economically, this is a feasible and economic power generation solution anywhere on Earth. This is a rendering, the one I have behind me, of our first commercial project out here in Oregon. It'll be 50 megawatts electric gross and 50 net. It's a little bit on the design here, but basically it's two inclined benches of wells, where in each bench you have a single injector and two production wells. We are trying to stage our approach to risk by having these wells not horizontal but inclined, which is easier on the drilling equipment at these high temperatures, and also enables us to abandon the lower parts of the well if we have a technology or a technical failure due to the very high temperatures and pressures. It's on the south flank of Newberry Volcano, which is a national monument. So there's been some challenges in the past with people working up here, but we've found that the BLM and Forest Service have been really good the last few years about balancing the need to sort of protect this very special place for public use and also allow for this type of cutting edge research. This is pretty outdated, but this is sort of a video of the project site from December that shows the well pad we've built, which is about 5 acres. And that pad will host this whole system there'll be a small separate pad a little farther south for the power plant itself, but we are getting 50 megawatts electric net from just this basically acreage you're seeing here. A little bit here on the technology gaps and challenges we have going forward. On the right, you'll see for our current project that's around 300 to 350 C, we can use a lot of the existing oil and gas technologies to create our reservoir and maintain it over 2+ decades. That's needed sort of to make the project economic, but sort of going hotter and deeper, we're going to be facing some challenges around the chemistry of the reservoir and not having tools for being able to model that chemistry and that sort of geometry of the fracture network. But this is something we're working on at Quaise and also in partnership with national labs. I think something that people get wrong about Quaise is that we're just this drilling company, but really we are a developer of these next-gen superhot rock systems. So it's a drilling technology plus these reservoir creation technologies. This last section is a little bit on sort of policy issues and the bipartisan nature of the support for this industry. We've been really fortunate in that both the left and the right have sort of found things to love about geothermal, and nobody's found things that they really dislike yet. On the right, you have supporters of the industry for national security and energy independence, the fact that we're leveraging the oil and gas supply chain and workforce, and that this is really an economically competitive type of electricity due to its always on nature. On the progressive side, people find reasons to like it because of the zero emission nature of these next gen systems, in particular, the fact that it complements renewables like solar and wind that are not firm, so that can work really well together to sort of meet the changing demands of the grid. Has a very small land footprint. It can coexist with existing land use for agriculture or natural resource or protection. There's also opportunities for critical mineral extraction and sort of bringing back onshore some of these key supply chains, not just for geothermal, but also other green economy industries. It's sort of a overview of what has happened over the last few decades in the industry. But in the 70s, during the oil crisis, there was a huge initial investment in geothermal. And a lot of that is actually what the industry was able to leverage the last 5 or 10 years to really see this explosion in interest and growth. It all dates back to that initial investment in the 70s and early 80s to do sort of resource characterization, resource mapping, drilling temperature gradient wells in all sorts of places. Unfortunately, in the late 80s and all the way through the 2000s, there was a real decline in support in the industry when oil prices came back down. It's only in the last 5 or 10 years that there's been sustained interest and investment because of success at places like Utah Forge and commercial successes like Fervo that have proven the ability to adapt oil and gas technologies for this geothermal energy purpose. This is a little overview of our main industry association called Geothermal Rising, and the sort of political end side of it is called the Geothermal Rising Policy Council. There's different organizations that have different sort of participation levels, but you can see we have a pretty broad coalition of oil and gas companies, think tanks, NGOs, geothermal developers, and service providers, all coming together to sort of set a policy agenda that we can advocate for with one voice. because I think one of our challenges is being such a small industry. If we're not all singing the same song on sort of our priorities here, it will get drowned out by sort of bigger stuff in other industries. But we had a really successful hill day fly-in this year, where we met with 127 separate legislative offices and agencies. Industry people were paired up. So I participated, and I was with someone from Utah Forge, someone from the New Mexico Geological Survey, and then someone from Baker Hughes, and we were all sort of there talking about our agreed upon talking points for the industry and our interest in seeing sort of this whole ecosystem succeed. These are sort of the main issues that we're working on today as an industry coalition. The first bucket is around permitting and permitting reform. The challenge that geothermal developers face is that it can take a lot longer to develop a geothermal project compared to something like a natural gas plant or wind and solar plus batteries, because we face up to 6 separate environmental reviews over the course of a decade, and many of these are sort of overlapping and redundant in different ways. And our goal as an industry is not to sort of remove any sort of environmental rules or regulations, but to really make sure that these are done effectively and efficiently in a way that also allows the industry to scale and compete with fossil fuels and other renewables. There was a suite of 8 bipartisan bills introduced in the House this year, all around these sort of permitting issues. You had some of the most left-wing and right-wing members of Congress sponsoring these, and everyone agreeing together to try to pass them as a slate, because we think all of these sort of work together to make this process better for the industry and for the public. We're also trying to get the category exclusions that BLM has implemented in legislative text. So there's more long-term security around that. And also trying to push BLM to standardize their practices around competitive lease sales for those public lands. We're also working on appropriations and funding. So trying to make sure that geothermal is treated as a real solution and player. In 25, there was only $120 million appropriated to the geothermal office at DOE, compared to over $1.5 billion for nuclear, about $1 billion for fossil fuels, and about $500 million for wind and solar. So we want to see a larger sustained investment in geothermal specifically, because we think that it has the potential to contribute something significant to our energy mix. We also want to make sure that BLM and the U.S. Geological Survey are being funded appropriately, so they can work on the really important stuff of making sure permits are processed timely and by experts, and also doing some of that really key early stage resource evaluation and mapping that enables the industry to come in later and show these types of data sets to banks and investors and say that, this is something that's really going to work. Also looking to continue to support R&D funding for next-gen technologies, critical mineral co-production, and resource assessment. Also, there's a huge potential to work with the Defense Department on behind-the-meter power generation for military installations. There's already 12 of these types of projects being worked on, but there hasn't been a sort of comprehensive report by the DoD, DoW on the status and the way that these things can contribute. They're looking a lot at small modular reactors, but we think this is a easier to permit and ultimately cheaper energy source. Our other sort of major priority is creating this bipartisan geothermal caucus. so that all of this work has a natural home among the legislators on the Hill in DC, and sort of build cross-party, cross-coalition support for a lot of these things that tend to be agreed on by most members of Congress anyways. It also sort of provide a venue for education and outreach to the staff. Quaise specifically has endorsed 4 bills this past year, and we're always looking for other organizations to jump on board and endorse these as well. The first one is the Next Gen Geothermal Research and Development Act, and this is sort of R&D funding for next gen technologies. A similar bill called the Hot Rock Act, which is focused just on superhot rock, also creates centers of excellence and workforce training programs. We're also big supporters of this GeoPower Act, which would create dedicated funding for commercial scale demonstrations. So full power plants testing out different technologies in different places around the US. Currently, there's $170 million allocated for testing specific components of systems. So that's a great already existing geothermal grant program, but the grants are chunked up into small pieces. So it's not enough to fund a whole project or enough of a project to really crowd in private investment as well. There's also this Geothermal Tax Parity Act, which sort of puts us on par with the oil and gas industry and allows us to count the depreciation of assets and drilling expenditures as tax deductible. And that's a subsidy that the oil and gas folks have benefited for a long time. And we think that we're doing very similar work, and it should also be applied to us. One slide here on Texas specifically. There's a great organization in Texas called the Texas Geothermal Alliance, or TexGEA, that we're big supporters of. They've put out these 2 great reports I'd definitely recommend, called The Future of Geothermal in Texas and The Texas Geothermal Landscape, and have also funded resource mapping for the state. And so you're seeing on this map here the temperature at 6.5 kilometers below the surface. And you can see there's actually a lot of potential for power generation across the state, especially in the Gulf Coast and West Texas regions. There's some Texas-specific policy issues around clarifying the way that geothermal energy rights are defined, making sure that the legislators in Texas understand the issues. So there's outreach and education work to be done. And then stuff around incorporating geothermal's baseload nature into the planning cases by like ERCOT. And so when they're comparing geothermal to another resource, they're not just looking at the LCOE, which doesn't always account for the firmness of the resource. And I have a few appendix slides here on millimeter wave drilling and how it works, but also happy just to answer questions about any of this content.
Okay. Can you all hear me?
Yep.
Okay.
Yes.
I've had some internet problems, so I don't believe you all have, but so I apologize if there was some interruptions. Waqar, go ahead. You're first.
Okay, great. Quinlan, thank you very much for a really interesting presentation. I've been around technology development quite a bit. So what I think about is, okay, how many miracles do you need to have to, succeed? And I'm sure that's what you're focused on. And so I was just thinking through in my mind. So on the drilling, you've got to get power to the gyrotron. You've got to get the cuttings out, and then you've got to frack the reservoir and create a reservoir where you don't lose too much water. So that's at least 3. that I thought of. What do you think? Are those the ones, or are there other things as well?
Yeah, I think those are the major ones. I think we've already answered the question about getting sufficient power to the bottom of the well. We've done some um, microwave transmission tests with the systems we've already designed, which are pretty early stage, basically to see how lossy the system is when we're sending the microwaves over 100 meters, and then using that to extrapolate um, how deep can we send this. And we are pretty confident that with our 1 megawatt gyrotron that's being commissioned this year, we won't have any challenge getting enough energy down to the rock target. I think the other questions around how do you circulate cuttings with basically how do you air drill at these depths, and how do you fracture a reservoir at these sort of novel under these novel rock mechanic conditions and pressures and temperatures are more open questions, but ones that we're actively working on at Quaise, and that the broader sort of ecosystem of national labs and sort of international research consortiums are also working on. So
Yeah.
our goal right now is to sort of push this one step at a time out here in Oregon, and then in 5 years or decade, start to bring this to that sort of 10-kilometer plus range.
Yeah, that's great. No, it's great that you're working on this.
Yeah. Stuart.
Okay, thank you, Quinlan. That was very good. Very informative. Do have a couple of quick questions, but I'll limit it to one. Everyone here expects me to ask a geology question, but I'm not. So CCL's flagship policy is putting a price on carbon. And the greater the carbon intensity, of course, the greater the price. And you said, or you asked, that if there were policies that Quaise and the Geothermal Coalition were working towards, they're looking for partners. I'm going to flip that and ask whether we could anticipate partnerships in approaching a price on carbon in the future.
Yeah, thank you so much for that question, Stuart. I think I am not the best person to speak on like an official position of Quaise or the industry. I can get you in contact with our sort of director of government relations if you would want a sort of firm answer on that. But I think it's something that Quaise would probably be interested in cross endorsing, but that the larger industry coalition may have a aversion to, since a lot of the industry is coming of funding for the industry, and operators are actually like oil and gas companies themselves. So probably one that I'd need to refer you to my government relations director on.
Thank you for your honesty with that one.
Cynthia? You're muted, Cynthia.
Super interesting. I would kind of need to understand a little bit more about what microwave drilling is, but that's not the question I'm going to ask. About critical minerals, that was brought up on one of your slides, that somehow this technology gives access to critical minerals. Is that a byproduct of an actual geothermal well, or is that a side application, a different application?
Thank you for that question. The case I was talking about was a byproduct of certain wells. So there's there's actually an active demonstration project in the Salton Sea area in California, where the geothermal brine that they produce happens to be very enriched in lithium. And so they're extracting that from the brine before they run it through a heat exchanger. Maybe it's after they run it through the heat exchanger. But that's sort of the opportunity, I think. A lot of the formations that have geothermal fluids or natural heat also enriched in some of those critical minerals. So.
Thank you.
Okay, Jim?
Quinlan, thanks for a very clearly illustrated talk. I don't recall what is your target TD temperature for the heat exchanging or the heat circulating that you envision?
Yeah, that's a good question. Thank you, Jim. At this project in Oregon, our first bench has a sort of average temperature around 315 degrees Celsius. And this deeper bench is going to go to 365, I believe. The long-term goal is to be at or above the critical point of water, which starts at 374 C. And that's because of that sort of step change in ability to extract heat. And I sort of also forgot to mention there's more advantageous power cycles you can take advantage of at the surface with that higher temperature water. So you have a more efficient generator at the surface as well.
Thanks. That's probably reasonable. Your early, a couple of years ago, some of the releases that y'all had talked about you were vaporizing the rock at the drill face. And every time I heard that, I go, well, once it gets up whole until it chills, you're going to choke yourself off. But if it just has to pulverize things until Stokes' law from your air drilling can carry it up, that solves that problem. And I hope that you have more. The Oregon, is that actually drilling obsidian?
We're drilling
If you can talk about it.
Assortment of volcanic formations. So it's called Project Obsidian because on the top of the volcano there's a very famous obsidian flow.
Well, I hope you have more luck than I did trying to drill obsidian rock mechanics samples way back there in graduate school, because it's tricky stuff. But it sounds like if you're doing mixed rock types, that's going to be good for some of the high heat flow volcanic areas. Thanks a lot.
Yeah, thank you for your question.
Go ahead, Bill.
Well, very, very interesting talk. Thank you, Quinlan. And we wish you success with your endeavor. I mean, this is a huge opportunity if y'all can make it work. One simple question is your demonstration video of the vaporizing the rock. What kind of rock was that?
That was a basalt. We find that we've been able to drill in a variety of rock types, but that the mode of drilling sort of varies from rock to rock depending on the mineralogy and texture of the rock. We've found that sort of the most success we have in high silica rocks with sort of a heterogeneous distribution and grain size. And we think that's got to do with the alpha beta quartz transition and sort of a way it might be inducing spallation instead of melting and vaporization.
Thank you. And the second thought is that, like Cynthia, I'd be very interested in hearing more about your millimeter wave drilling. And if we run out of questions, if you could get into the appendix slides on that, that'd be cool.
Yeah, happy
Thanks.
to.
Okay. Mark, go ahead.
Hi, Quinlan. Yeah, I was sorry, I'm getting an echo, but I'll try to work through it. You mentioned the Texas Geothermal Energy Alliance, and I'm wondering in 2025, do you know if the Texas legislature passed anything that was favorable to geothermal, or if there's any hope for that happening next year?
I don't know. My most of my work is not on any sort of policy stuff. I work on it occasionally, but usually it's like at the federal level. I do know that TextGea has helped us set up a sort of a site visit for legislative staff in Texas to that drilling demonstration site in Austin, and so they've been really supportive in that regard. I don't know what sort of accomplishments they have to show for all of this work. They've only been around for a few years as well. So,
Go ahead, Bob.
I'm not confident in what I think I know about geothermal, but you can advise me. It's my understanding that there are currently some of the facilities doing advanced geothermal already either in process or functioning. But what you're looking to bring to it is a cheaper form of drilling that would bring the cost down to be competitive with other renewable energies. Is that correct?
yeah, that's right, and not just renewables, but fossil generation too. So, that's sort of natural gas turbines have been sort of the first choice for a lot of utilities in the last couple years, and we think that's sort of the target we need to be competitive with.
Okay, and in Texas, there are fewer permitting requirements land, I believe, so that the do you have any sense of how close you are to making this commercially viable? Are you in the project demonstration phase?
Yes, so this site in Oregon, we are going to be drilling the first commercial well in less than a month, and we've already signed a power offtake agreement for this and future projects. We are not able to say who that's with yet, but that's already been sorted. So this is really a commercial project, not just a R&D or demonstration project.
Okay. Thank you.
Okay, I'm going to take host privilege right now just because I want to ask a question. And I may have missed this because I was bumped out for a bit if you talked about a millimeter wave drilling. But with like a 15 to 20 kilometer depth hole, which is, mind-boggling. But, with conventional drilling, you got the issue of hole collapse. And so I was just wondering, how do you clean a hole out if your hole happens to collapse? And do you you case these all the way down? I mean, or maybe you didn't touch on that much in the millimeter wave.
Yeah, thank you for that question as well. I'd start by saying we will be casing all the way down. I know some of our communications early on in the history of the company talked about this self-forming vitrified liner out of the glass that's created when you melt the rock, but we found that really is too challenging to engineer into something stable. Right now, it's a sort of active research topic area in the future, but right now we're planning on casing to TD. And the circulation question is also a good one. I don't know if we worked out exactly what sort of gas or fluid we'll use when we're going to these more extreme depths, because I think air drilling is only sort of proven to a certain point. So also a good question, but that's the type of stuff that the engineers in Houston are working on.
Wow, thank you. You're cutting edge for sure. Mark, go ahead.
Yeah, thank you. I had a question about the millimeter wave. Are there materials or metals that you have to avoid when you're drilling deep? Does that limit the areas where you can actually drill?
Um, Not in the rocks themselves. I think the one thing we would be concerned about are oil and gas formations or any sort of like really carbon rich rock that is potentially combustible. But our goal is to drill with conventional drilling technology sort of through those sections of um, the well, because that's where we think the conventional system will be more economic anyways. And it's only sort of when we're in this crystalline sort of granitic basement rock that it makes sense to switch to this microwave based system.
Hey, Dan? Oh, you muted yourself, Dan.
Yeah, I think I read that you for your testing you use a low power gyrotron and to drill the 4-inch hole, 4-inch diameter, and you plan on using a more powerful gyrotron in the future. There's only a few available. Do you know if is that what's going to occur? And will there be enough gyrotrons to get these projects done once you get rolling?
Yeah, that's a very good question. That's something I think we think about a lot and stress about a bit. There's not a robust domestic supply chain for these systems. They're pretty specialized and not used that widely outside of fusion experiments. So it's been a challenge to develop or procure gyrotrons that will work in field conditions, because these are really white glove machines that are meant for use indoors in a lab condition, not something that you take out to the field. But I would say we were testing last summer in Marble Falls when there was the really extreme rainstorm, and also through the winter when there was snow, and in the summer when it got over like 110 degrees outside. So the way that we've engineered our version of these systems, we think they're pretty adaptable to all sorts of field conditions. We've already drilled 100 meters, so I think it was like 350-ish feet with a 100 kilowatt gyrotron. And we're going to be drilling about 3,000 feet with that system this summer. The same time, we're commissioning a 1 megawatt gyrotron that will be used for our first commercial applications.
Okay. And before we move on, I just want to
Thank you.
thank Dan for helping me contact Quinlan and arranging this webinar. So, Tom, go ahead.
Oh, hi. Yeah, thanks. This is really, really useful. I'm glad you're casing the well. Are you casing both ends, the discharge piping also?
Yes. Yeah, that's probably the more challenging side, because when we're drilling, we're trying to keep the temperatures down. And then it has to be able the completion, the cement and the casing needs to be able to withstand a sort of 200 C plus temperature swing for when then we're extracting the heat. So that's probably one of the bigger challenges in the industry too, is finding cements and casing material that can work at these temperatures and under sort of large swings in temperature and pressure.
So you're gonna meet the intake and discharge. Okay. The other thing is, do you anticipate any problems with tailings? If you run through, thorium or lithium or strontium or anything weird?
We do not, and the microwave process doesn't have any effect of making the cuttings more dangerous in any way than a regular piece of rock is. So a lot of rock is naturally radioactive, but in the same sort of way that like a banana, because it has a lot of potassium in it, is naturally radioactive, it doesn't really pose any human health risk outside of we do be pretty careful with the tailings we produce, because it's very small fragments of rock that if you were to breathe them could cause silicosis. So we're still very careful with the tailings and have just been storing them on site for this first demonstration.
Okay, thank you.
And before we go on, I think we're at our time limit. Quinlan, do you have a few more minutes, or you just keep going? So, everybody, we're just going to go until we run out of questions, I guess, or we're not going to go forever. But go ahead, Jim.
Yes. Following up, I believe you said the target for an individual borehole generation plant, if you're able to get to 300, 350C, I think you said 50 megawatts.
So this first system will be 2 benches, 3 wells in each bench, so 6 wells, and that produces 50 megawatts net. The goal in the future would to be even better by going to higher temperatures. So the main thesis of the company is really not that the drilling technology is sort of the pivotal thing, but the ability to access higher temperatures that are more efficient for both heat extraction and power generation. That's how we really bring down the cost and scale up. And it's just that in order to do that, you sort of need a new drilling technology as well.
Do you know, I mean, roughly, a lot of times you hear these quoted as how many households it could support or whatever. I don't know if that's a number you have off the top of your head, but it strikes me the real plus of this, if you only need like a 5 acre footprint well pad, is you could do this in a either active or abandoned shopping center parking lot, and that way, if it's used nearby, you don't have to worry about grid access and some of the other things, for the more uh, prospective in the Western U.S., but a lot less populated areas. So that, and it was interesting that the NREL map of in Texas, in the area, had a higher temperature potential at the target depth of, I think, 6.5 clicks for the Sabine uplift than for the Central Texas granite area. And I guess if you can get that deep in the Sabine uplift, if, Tyler needs the energy or whatever, there are at least volcanics we know way down there. And so that could be perspective, but the potential for decentralized really looks like the leg up, that you don't have to be utility scale. You could be neighborhood or municipal scale with just a few months of drilling disruption and a little bit of open space. Thank you.
Yeah, thank you. And I would just add, I think that ability to go anywhere is really the exciting part about what we're doing and what some of the other people who are trying to do these higher temperature systems in more places by going deeper are doing. Because historically, geothermal, I think one of the things that's limited it is you were really constrained by where you found the resource. And a lot of these resources that are naturally occurring are in, rural Nevada. And that means you'd have to build a really expensive interconnection. Just even if you have a perfect resource, it might not be feasible to send power from there. But what we're hoping sort of unlocks this ability to scale the industry is being able to put these plants anywhere, where the geology is not really the dictating factor anymore, but it's one of many that's used to factor into a decision about where to site the plant.
Right. You could do it based on potential demand rather than most favorable geology. Thanks.
Okay, well, it looks like maybe we have run out of questions. I have put in, first off, I want to thank Quinlan. This has been great. This has been very, very informative and been wonderful. Um, but if you would like to get credit for attending this session, within the chat, you can click on that and it'll give you, it'll log your attendance automatically. And Cocktails and Conversation is taking the summer off. So I don't have the next session planned or anything, but it'll be the end of September. And we'll come up with a topic and get that out to you later. Um, yeah, so thanks once again, Quinlan. This is, like I say, it was just, I think everybody here just thought it was excellent, very informative. And you're always welcome to come back if you want to get into the microwave further. We'll make time for you for sure.
I was going to say you could sign up for email updates, like I did. I get regular updates from Quaise.
And we can send that out.
Their progress.
The other thing is, I think it's worthwhile for CCL to be aware of those bills that you had listed that you would like to get some support for. If we get that connected to our national group up in Washington, D.C., that's something I think that is very possible, that makes a lot of sense, particularly with the bipartisan nature of the technology. So that might be something, Quinlan, that if we could keep in touch with you on that side of it, or you can find somebody that within your organization that could, we'll get the right people connected, and we might be able to support that.
Yeah,
And
happy to work
permitting
on that.
reform has been a focus.
Yeah, yeah. But they had specific things related to geothermal that was probably outside of that. So, yeah, it's very worthwhile. Okay, well, everybody have a great rest of your weekend and great summer, and see you in September as the song goes.
Thanks, Roger.
Thank you so
Thanks,
much,
everyone.
Quinlan.
Everybody. Thanks.